Let me first say thank you to Hossein and the organizers for the invitation to speak here. Pleasure to come to the desert in the middle of winter. The focus in my research group in Madison is on using Rydberg atoms for quantum information, for quantum gates, quantum computation, quantum communication, and to do those kinds of things using the strong interactions we get by exciting to Rydberg states, we need to have quantum state control of the atoms when they're in the ground state and also when they're in the Rydberg state. So this, we need to control not just amplitudes of quantum states, but also phases very precisely. So what I'm going to do in these lectures is tell you about techniques that go into performing quantum computation using Rydberg state interactions. And so I'm going to start today with some background, which is perhaps a mundane topic, but go into some detail about the laser excitation of Rydberg states and how you do this in a precise way with attention to the phases of the quantum states, do this coherently. Just to give you a preview, I'll then tell you about trapping of ground state atoms, but also trapping of Rydberg atoms, which is something we partially achieved in the lab, but something that's still being developed. And ultimately, we really want to trap the Rydberg states just as well as we trap the ground states in order to perform quantum information processing with high fidelity. And then I'll tell you about various quantum gate protocols and entanglement generation, both things that have been demonstrated and also ideas for future experiments. So, starting with the excitation, this is an overview of what I'll try and cover in this hour. We're running a little bit late, but I'll try not to cut any further into lunchtime. So I'll just give you some overview, how you actually calculate these rates. If you're designing an experiment, you need to know how to calculate the rates of these Rydberg excitations. I go through some of the different methods that can be used, 1, 2, 3 photon. Show you some experiments with coherent oscillations between ground and Rydberg states, and also talk a bit about adiabatic pulses, ways of doing the excitation which are insensitive to uncertainties in the experiments. Okay. So to perform experiments using Rydberg atoms, we need to, of course, excite the Rydberg states. 1, 2, and 3 photon techniques are widely used to access low angular momentum, low L Rydberg states. There's also interest in exciting high L or circular states that require some special techniques that I'm not going to cover. As I said, for applications involving quantum information, we need the excitation to be fast, coherent, and state selective. And I'll show you some details about that. And with modern laser systems, the coherent excitation is relatively straightforward. Some of this material I'll go into great depth with and really show you the details of how you think about these things. Some of the topics I'll just mention and point you to some literature, but won't have time to go into details about. So basically, if I take an alkali atom as my prototypical example, we start in an S state. With 1 photon, we can go up to a P state, which we've already heard about. With 2 photons, we can go through a P state and end up in S or D states. And if I took a 3 photon excitation, we could go to end up in 2 photon states into S or D, so 3 photons would take you to P or F. Of course, we could do 4, 5, or 6 photon excitation if we wanted to. No one has had any particular need to do that so far. How do we actually calculate these rates? Well, so this is sort of basic atomic physics. We start in the ground state, we're coupling to an excited state. We have a light beam, say a laser beam with an intensity related to an electric field that defines a Rabi frequency by the product of the electric field and a transition matrix element. And depending on the polarization of my electric field, that transition matrix element in a spherical basis involves a component of the position operator of the electron. These are the 3 spherical components. And then I can use the Wigner-Eckhart theorem to reduce this matrix element to some angular factors times a reduced matrix element. In actual quantum state experiments, there's an additional complication, and that we're typically transitioning between states in different representations. That is, we're starting in a hyperfine result state and the ground state, and in a high-end Rydberg state where the hyperfine interaction is negligible, we're ending up in a fine structure state. So there's some additional algebra involved in coupling between those 2 bases. The reduced matrix element, then if we're thinking about a transition from hyperfine to hyperfine, we have to go through several steps of angular reduction to eventually end up with a radial integral. So apart from all these different angular factors, we need to calculate these radial integrals determined by the overlap between the ground state wave function and the Rydberg state wave function. So before we actually calculate them, how do those integrals scale? Well, if we can estimate the integral quite simply in the limit where the Rydberg state is highly excited and much greater than 1. The integrand for L states greater than 0 vanishes away from the origin. For Rydberg S states, we know just by looking at the hydrogenic form for the wave functions that the probability of finding the atom at the origin in S state scales as 1 over n cubed. And therefore, the integral, just by dimensional analysis, is going to scale as the atomic length, the Bohr length, divided by n to the 3/2. It's the wave function, not the wave function squared, is an integral. So we know that going from the ground state up to a highly excited S state, this integral should scale as 1 over n to the 3/2, and that scaling is maintained also for the higher L states, not just the S states. To actually calculate the numerical value, there's different methods we could use. There's a semi-classical WKB methods, and there's a number of variants of this when applied to Rydberg atoms. My personal favorite is this paper by Kalakis from 20 years ago or so. We can use Coulomb wave functions, that was quantum defect theory, Alice Eaton, or we could use model potentials to calculate the wave functions. And you can find a very extensive review of different methods that have been used in this physics reports from a couple of years ago. So let's actually look at some of these wave functions. Here's, say, a cesium ground state wave function calculated from quantum defect theory. Here's a 50p wave function, of course, much further out away from the nucleus. The product of these is what enters into the integral, and that integrand is, of course, localized near the core. So we only need to be concerned about the product of these two wave functions close into the core. Here's a calculation going from 6s up to np. These blue dots here are using a WKB approximation. The integral actually changes sign as you go through different values of n. And this is the absolute value of that integral. And this red line here shows the 1 over n to the 3/2 fifth. So you see, as soon as you get up to around n equals 50 and beyond, this asymptotic scaling is actually quite accurate. It scales as 1 over n to the 3/2. Although the absolute value of the WKB method going from ground to Rydberg is actually not that accurate. We can compare the WKB calculation with a calculation based on Coulomb wave functions, using the known quantum defects of cesium, and there's a quantitative difference of about a factor of 2 here, okay, at high n. So although the scaling is good and captured by the WKB, you actually get a quantitative number that these Coulomb wave functions are more accurate. How do I know that this red calculation is correct and the blue one is wrong? Well, actually, that might be hard to be sure about, but my belief that the red calculation is correct is actually based on experiment, and that we've measured these rates in experiment, in controlled experiments, and have been able to reach agreement with this red curve to about 5 to 10%. So that tells me that's more accurate than the WKB. Actually, I forgot to say I would like to try and make this as interactive as possible, so please try and think of this not as a conference presentation, but more like a classroom lecture, and feel free to interrupt me as I go along if you have questions. So, one photon methods to access p states. For high-lying Rydberg levels, these are pretty short wavelengths for the alkali atoms, 300, 320 nanometers for rubidium and cesium.
Can I interrupt?
Sure.
For the previous slide, maybe with your WKB, I was wondering, is that with the correction, like for the 0-point motion, we have basically what's called Langer modification.
Which modification?
Langer modification to account for the additional centrifugal barrier, especially for S states. I think it adds basically 1/2 to each angular momentum, I think for S states it makes a big difference, and it could be that for the 6S, you do the longer modification, you get much better agreement. I'm not sure if that's taken.
I'm not sure. My feeling is it's not included. So when I say WKB, I'm using the theory in this paper with a sign error corrected. So we'd have to talk about it. But there's probably 15 different WKB Rydberg calculation papers. And I have not carefully compared all of them, I have to say.
Because there's one very basic modification to WKB, to the standard WKB, which is like a quantum defect. And that takes into account that basically you can only make a transition to WKB or if you have a range of your coordinate which goes from -infinity to +infinity. Only then the correspondence principle works. And since you're dealing with radial systems, that's not the case. And then you get already on the lowest order a correction, which takes into account that you have a node at 0. And this is like a quantum defect for the space.
Oh, that's interesting. Of course, as you know, the quantum defects are included in this WKB to get the energies. You have to input them to make this calculation. Maybe we could talk after. I mean, I would expect that these two curves should be a lot closer to each other,
I would
if
guess
done correctly. Maybe we could discuss this. Thanks. Okay. The one photon excitation tends to be very short wavelengths for the alkalis. It's not done so commonly. There actually have been experiments in the last year showing coherent excitation at Sandia Labs, Grant Biedermann's group, using one photon excitation in cesium. And I know there's efforts underway to do this in Munich at blockade. There's also strong Doppler sensitivity when you use a single photon excitation, and I'll come back to this. Nonetheless, here's an example of one photon excitation of a rubidium 63p state from the Hensch group. And they used a quantum amplification effect in the B system. The idea here is you drive the atom simultaneously from 5s to 63p, but also on this strong first resonance line to the 5p 3/2 state, because the lifetime of the Rydberg level is much longer than the lifetime of the 5p state. When you have successful excitation, it blocks the fluorescence on this transition, and so that gives you a kind of quantum amplification. And so you monitor the 780 fluorescence to deduce whether or not you've excited the 63p. And with co-propagating beams, you can do this in a Doppler-free way and actually extract a Doppler-free profile for the 5s to 63p excitation. Two-photon methods are much more widely used these days. And one has to, in two-photon excitation, be concerned about a couple issues: Doppler, residual Doppler, and also AC Stark shifts. With the two-photon scheme, we can use longer wavelengths. So typically, in an alkali, we're going from the ground state to the first or second excited state up to the Rydberg state. We can reduce the Doppler by counterpropagating these two fields. The drawback for this is that you get spontaneous emission from this intermediate p state. If we detune substantially from the p state, then the two-photon Rabi frequency is the product of the one-photon Rabi frequencies divided by twice the detuning, and you can readily calculate the spontaneous emission in a pi pulse, which gives you full transfer of population from the ground to the Rydberg state. And if you do that, you'll find that the spontaneous emission probability in that pi pulse is governed by the ratio of the line width of the intermediate state, gamma p, divided by the detuning times this function of the ratio of the one-photon Rabi frequencies. So that spontaneous emission probability is minimized, and that's an optimal point for quantum operations. It's minimized by setting the one-photon Rabi frequencies equal. And that's also advantageous for minimizing Stark shifts, as we'll see in a moment. So we set the one-photon Rabi frequencies equal, and then we get a expression for the Rabi frequency relative to the spontaneous emission probability and the one-photon Rabi frequency. So that's this expression up here. We can see it now. And therefore, the Rabi frequency is proportional to the spontaneous emission probability, the power in your laser, divided by the line width. So if we have enough optical power, we can have fast Rabi frequency with small spontaneous emission. So common wavelengths are well known for rubidium and cesium. If we take the first resonance level, the first photon is in the near infrared, the second photon is in the blue. If we go through the second resonance line, then the first photon is in the blue, and the second photon is in the near infrared. And this can be advantageous for getting fast excitation, just because if I go to the second resonance level, the line width is smaller. The lifetime is longer at that state, and so if I make this line width smaller, I get a stronger Rabi frequency for the same spontaneous emission probability and the same power. So technically, that can be advantageous. And here you see an example kind of showing that comparison. This is for rubidium. If I want to work at fixed spontaneous emission probability, say 10 to minus 2 or 10 to minus 3 for high fidelity excitation, then I need a certain power in my beam as the Rabi frequency increases. If I want to work at 10 to minus 2 spontaneous emission and get up to 10 megahertz to a certain level, here I needed 75 milliwatts in blue. If I do the same thing through the second resonance line, I greatly reduce the power requirement on the second laser, now down to a much lower power level. So that can be advantageous. And this kind of second resonance excitation is now being done in a couple different groups, Pisa, Stuttgart, and also Madison. The other issue with this two-photon excitation, another issue is Doppler broadening. If we co-propagate the two photons, then we pick up the full Doppler shift, so we get a Doppler frequency shift, which is the atom velocity times k1 plus k2. And if I take a cold atom with, say, a 10 centimeter per second velocity, we get about a third of a megahertz here, a Doppler, which is a fair amount. If I counter-propagate these two beams, then the Doppler shift is the difference of the wave vectors, and I can greatly reduce the Doppler broadening. So you see that here. This is the Doppler broadening in frequency units versus the temperature of the atoms for co- and counter-propagating beams. So the counter-propagating case is to be preferred, and that becomes even more clear if we look into time domain. So here's time domain calculations of excitation of rubidium with a Rabi frequency of 1 megahertz, or a two-photon Rabi frequency of 1 megahertz, and we're averaged over the Doppler curve. For 150 microkelvin atoms, it works really well for counterpropagating, not so well, but not too bad for 1 or 2 cycles. For co-propagating beams, for these much hotter atoms, 10 millikelvin, I'm really not going to be able to get coherent excitation at these kinds of Rabi frequencies. Okay. And here you see, even for the cold atoms and the counterpropagating case, there's this line here going down. This is just the limit set by spontaneous emission from the Rydberg state. There's also the issue of AC Stark shifts. So the two-photon transition is AC Stark shifted by the excitation beams, and that AC Stark shift is sensitive to intensity noise on the lasers and also the atomic position under the spatial profile of the envelope of the beam intensity. And so that gives some inaccuracy to the high pulse excitation, which is a problem for quantum gate implementations. And so you can see an example of that here, where we're looking at the rubidium 55S state. At low power, we have a excitation frequency here. Just turning up the power, this frequency has moved over a few megahertz. And when calculating this two-photon AC Stark shift, we have to consider the contributions onto both the ground and the Rydberg states. So if I am detuned, if the first photon has a higher frequency than this first atomic transition, that will shift the ground state up, and that's a near resonant transition, so there's a strong interaction with this first photon and the ground state. The second photon interacts mainly with the Rydberg level, that will now be at a lower frequency. If the two-photon transition is resonant and the first photon is at a higher frequency, then the second photon is at a lower frequency, so that also shifts this up. So those two contributions add. There's also smaller contributions, which is the off-resonant contribution of the first photon of the Rydberg state and the second photon on the ground state. In many cases, those are going to be negligible. So that shifts this transition. If we want to make things, I might have said part of this wrong. Let's see, this first photon, if I'm blue detuned here, shifts the ground state up. That means this is red detuned, which, so the second photon here actually shifts the Rydberg state down. So if I want these things to cancel, that's right, close together, I just have to set the one photon Rabi frequencies equal, and then that cancels the dominant contribution of the AC Stark shift. So this point of setting the one photon Rabi frequencies equal minimizes the spontaneous emission from the P state and also minimizes these AC Stark shifts. So that's really the optimum place to operate. Okay. Actually, it's maybe worth knowing that you can, in principle, cancel both the Doppler and the AC Stark shifts together using a near-resonant technique. And that's because the Doppler shifts depend on velocity, and the AC Stark shifts depend on detuning from the intermediate level, which therefore also depends on velocity. So you can actually cancel both at once. This was pointed out by the Cohen-Tanucci group quite a long time ago, and they demonstrated this in a vapor cell, that by tuning near an intermediate resonant level, you could simultaneously cancel AC Stark and Doppler broadening. That's interesting, but it turns out not that useful for these kind of quantum gate experiments because it requires tuning in very close to this intermediate level. Doppler shifts for cold atoms are not large, and to minimize the spontaneous emission, we want to be gigahertz detuned from this intermediate level. So it turns out, again, although interesting, not all that useful for quantum gate experiments. Okay. You can also use 3-photon methods to access other levels, and 3-photon excitation has also the nice feature that you can cancel Doppler shifts using the different directions of the 3 photons. And you can also choose levels with the additional flexibility of having 3 photons such that they're all in the infrared, so you can derive them from IR laser diodes, which simplifies some of the laser setup. So this was, there's a nice paper from the Novosibirsk group from a couple of years ago, which shows that if you take a 3-photon excitation, consider general K1 plus K2 plus K3 equal to 0, that would cancel the Doppler effect. And there are coplanar solutions. So there's some examples here, particular geometry with all 3 beams in the plane, which will give you Doppler-free excitation. And so that would allow you to go outside the cold atom regime and actually get Doppler-free excitation, for example, in vapor cells. Well, there's an example diagram here for video. So here's an example from that paper comparing 1, 2, and 3-photon excitation, Doppler broadening effects for different temperatures of atoms. If I have 0 temperature atoms, there's no Doppler effect. I can have nice ground Rydberg oscillations for all cases. As I increase the temperature, here going from 0 degrees up to 300 K in the last row, you see that the 1 photon falls out first. Here it is about 1 millikelvin. The 2-photon oscillations persist a bit further. And the 3-photon, using these cancellation geometries, can give you very nice oscillations up to Kelvin-like temperature. So an example of an experiment from Pierre's group in cesium. So they used the Mott laser at 852 nanometers to go up to the first resonance level, an infrared laser diode to go up to a 7S state, and then a near-infrared high sapphire laser to go up to the Rydberg states. And for this experiment, they observed about 10 megahertz line width, and this was substantially broadened by interactions in this case. You can also do 3-photon excitation with 2-photon degeneracy. An example of that is these 2 degenerate or near degenerate photons taking you up to a D state, and then an IR photon up to the P state. Again, this was rubidium. So let me go through a couple experiments that have been done showing coherent oscillations between ground and Rydberg states. The first experiments in optical excitations of Rydberg atoms, I guess, were from the 70s and early 80s. There's a nice review of earlier work in this by Roach and this book edited by Barry Dunning. One of the first experiments I came across in the literature is this work on spectroscopy of Rydberg states of alkaline earths. And this is 1973 data, resolution about 1/10 of a nanometer, looking at this data, which was taken using pulse dye lasers, I guess. Sorry, neodymium glass laser system, so pulse laser system. Very well-known work from the Kleffner group, studying the stark structure of Rydberg states. This was 3-photon excitation, 2 driving photons, but an intermediate decay. So they went from 6s to 7p when looking at cesium, and then spontaneous decay, and then up with a 10 nanometer photon to a p level. And here you see late 70s data, resolution about 10 gigahertz on these stark scans. High resolution 2-photon excitation, we see here from the Reithel group from about 10 years ago, with now about just a couple megahertz resolution. This was a study of all the count splitting of the 2-photon excitation. So you see as you increase the intensity of one of the driving fields, you see the splitting of the excitation into this doublet, and so this lets you quantitatively determine your Rabi frequencies. Coherent oscillations in the time domain between the ground and Rydberg states were perhaps first shown in this paper from the Weidemuller group in Freiburg at that time, with about 100 atoms showing excitation probability starting in the ground state, going up to the Rydberg and coming partially back down. And this was a sample localized more than a magneto-optical trap, so it's a sample in an optical dipole trap, but a many atom sample. And so you still have issues with different atoms in the sample, seeing different local electric field strengths because of the spatial distribution of the exciting laser beams. The geometry was such that they had a broad red beam propagating to the left and a localized blue beam propagating to the right. And then the atoms are also in a dipole trap, so there's a overlap of these 3 beams defining the excitation volume, but there's still some spatial variations, and you see not a full contrast oscillation, so it comes up and comes partially back down. This may also be partially due to interactions in this cold sample. You can also see time domain oscillations in much hotter gases. This work from the Stuttgart group, Faust group, using very high intensity pulse lasers, giving oscillations in nanosecond time scale. If the oscillation frequency is fast compared to the Doppler spreading, then you can see oscillations despite the Doppler effect, and you see that here on the nanosecond time scale, where the transmission through the cell is oscillating here on a couple nanosecond scale. This is examples now with single atoms, which are well localized under the spatial profile of the exciting laser from our group in Madison, in collaboration with Pat Walker. So you see the starting with an atom in the ground state, going up to a Rydberg state, and back down, and you start to see very high contrast here. And more recent data from a couple years ago, if you tweak everything up, you really can do coherent oscillations from the ground state to the Rydberg state and back with amplitudes above 95%. So this is for a single atom, and this is corresponding work from the Balso group, also with single atoms from the ground state to Rydberg and back for several different conditions. Okay. The experimental approach that we use to get these high contrast oscillations relies on good stabilization of the lasers. So we have very high finesse optical reference cavities that are temperature stabilized and sitting in a vacuum. And these reference cavities have line widths at both frequencies that we're using of about 5 kilohertz. And then the lasers are narrowed to a fraction of that line width to several hundred hertz. if we're doing a Rydberg pulse with a microsecond time duration, the inverse of that is a megahertz frequency. And if we want the relative phase of the two photons to be well defined on that time scale, we need sort of kilohertz line widths on the lasers. And so these are several hundred hertz lasers, so we're within that limit. And that can be checked by building two of these and then feeding them together. Okay. So just having cold atoms, well localized, well-defined spatial profiles, and well-defined frequency and phase characteristics of the lasers is still not quite enough to observe these coherent sinusoidal oscillations. We still have to think a little bit more about the states that we're starting from and ending up in. And that's because if we don't have well-defined quantum states, then the Rabi frequencies will be different just because the overlap integrals are state dependent. So for these high contrast ground Rydberg oscillations, we're starting by pumping into a well-defined state. We pump into f equals 2, m equals 0 in the rubidium ground state. And then there's a 2-photon signal plus excitation up to the 97D state in this example. The ground hyperfine state we're starting from is a superposition of the electron spin being up or down. And so with two sigma polarized photons, we can end up in a fine structure state, 97D, the hyperfine splitting is order of kilohertz, so that interaction is negligible compared to our megahertz Rabi frequencies, but we can end up in either the m sub j is +5 halves or +3 halves, because the electron spin is starting in spin up or spin down, so we can access these two states. And the Rabi frequencies are different for coupling to those two states. And so to get sinusoidal oscillations, you have to also select one of those states out. And so we do that by applying a biased magnetic field. This is the, if you will, this is the Zeeman map of the 97D, including the fine structure splitting. So you have the 97D 5 halves with its 6 Zeeman states, and the D3 halves with its 4 Zeeman states. And so what we do is we work at a bias field of about 4 Gauss in this example, which splits these two states, which the laser will couple the ground state to. It splits those two states by about 5 megahertz. And so therefore we spectroscopically isolate just one of these states. There are methods of selecting a single Rydberg fine structure state without this kind of field isolation by choosing the intermediate state, the p state, to have a lower angular momentum, and thereby by selection rules you only get up to one Rydberg state. But that's a slightly different discussion. We can also check the coherence of the Rydberg excitation by performing a Ramsey experiment between the ground and the Rydberg state. So we start in a ground state, we do a pi/2 pulse, put the block vector on the equator, where now the block sphere is defined in the basis of the ground state and the Rydberg state, wait a variable time, do another pi/2 pulse, and then measure the probability to use the ground state. And if we do that, we get our Ramsey interference pattern, and this has a decaying envelope, which we can use to define a T2, which in this case is about 3.5 microseconds. What's contributing to that finite coherence time? Well, it's basically two effects. One is magnetic dephasing, and the other is Doppler effects. We have strong magnetic dephasing because the two states we're going between have a linear differential Zeeman shift. The linear Zeeman shift in the m equals 0 state and the ground state is essentially 0, but there's a linear shift in this m5 half state. So we have a strong sensitivity to magnetic fields. That's part of the decay. And the other decay is Doppler, and that it's not Doppler-free excitation. So as we wait longer and longer time in the Rydberg state, the atom is moving relative to the interference pattern of the two beams, and that gives an additional phase that we have to average over. We combine the T2s from the magnetic and Doppler broadening, and that gives us our total decay profile. Just a few microseconds. So this is a non-negligible contribution to the error we think about doing quantum gates on, say, 1 microsecond timescales. 3.6 microseconds is not infinitely long compared to 1 microsecond. And so to reduce this, one needs good magnetic stabilization, and also sufficiently cooled atoms. Let me then talk about adiabatic pulses. That's another way of doing coherent excitation. So this overlaps with the topic of ensemble blockade, which I think you'll hear much more about from Charles Adams. I'll just touch on it in the context of these adiabatic pulses. Suppose instead of exciting a single atom to Rydberg level, I excite with a many-atom ensemble, and I apply my Rydberg excitation lasers to that ensemble. Well, if I'm in a situation where I have blockade, we haven't really talked about blockade yet, but if I'm strongly blockaded, and due to the interactions between Rydberg excited atoms, I can only excite one Rydberg atom at a time. And therefore, this many-atom ground state will couple to a superposition of these different states, where in each ket here, one of the n atoms is Rydberg excited, and all other n-1 atoms are still in the ground state. And therefore, the quantum state describing this situation is a superposition of each of these kets R sub j, where R sub j refers to just the jth atom being in the Rydberg state. And then for normalization, I have to divide by 1 over root n, the number of kets. Okay. So I can think about a two-level system where one level is all atoms in the ground state, and the other level is this superposition state of one of the n atoms being Rydberg excited. What is the Rabi frequency for coupling between these two states? So each one of these states couples with a Rabi frequency omega, each one of these kets does, but there's a superposition of these in the total state, which I'm calling R bar. And so the Rabi frequency is the proportional to matrix element between the ground state and this many-atom singly excited state. So there's each ket in the superposition couples with a one-atom Rabi frequency, and then each ket has this 1 over root n normalization, but there's n terms